So we explained why the rules are what they are, but here we're just going to do some sample problems. So if you notice the exponentials, the logs, the natural logs, and then the derivatives of the trig functions. So if we look at this one here, f of x is equal to 2, 3 to the x plus 5 e to the x. They're the same as the power rules. We're taking them individually. But because the base is not the variable and the exponent is the variable, we have to use the exponential function rule. So we're going to take them in part. We're finding the derivative. So the 2 is the coefficient, the 3 is the base, and the variable is the exponent. You are no longer allowed to multiply the 2 and the 3 to make it a 6. They're separate. This is the coefficient. This is the function. So when you're taking the derivative of it, what you're going to get is the 2 stays the same as any derivative, and then you're going to take the derivative of the function 3 to the x. So the coefficient always gets multiplied to the derivative, so the derivative is going to be a stretch. So we're still going to keep the same function, and we're just going to stretch it by ln of 3. So the ln of 3 and the 2, this has become the coefficient of the function 3 to the x. So this is, I could put 2 times ln of 3 into my calculator, and I am going to get, since ln of 3 is 1.9, 2 is going to be approximately 2.18 or something like that. So this is the coefficient of 3 to the x. So that's the derivative there. The derivative here is going to be, on the second term, it's going to be plus 5 is the coefficient, and then we take the derivative of e to the x. E to the x is a function. It's not, because it has, it's not a constant, the e, because it has x as a variable. So it's going to be ln, oops, I did that again, ln of e to the x. You could skip this step. This is just 1. So we're just going to get 5 e to the x. So the derivative is just that. Derivative here. This one here, that is the power rule. So that's just going to be 3. And then this one here, again, leading coefficient, not leading, but the coefficient is going to be negative 2. This here is the function 4 to the x. So we're going to do ln of 4. So this becomes the new coefficient times the function 4 to the x. So this here, I cannot combine these two because these are separated by a minus, and anything that's multiplied is attached to the 4x. So this is separate from that. So we do not combine these two together. And so that is your derivative right there. Here, k is the constant. So that means that x is going to be the variable. It tells you that right there, and it tells you that k is a constant. So this here is the same thing as saying e to the 5 plus 5 to the x. The one that's going to be changing all the time is the x. The one that's going to stay fixed is the constant. I could choose any number for k, but it's going to be fixed throughout the whole thing. The variable that's changing is the x. So since this is a constant, e to the 5 is not e to the x, this is just going to be 0 because it's just a constant. And this one here is an exponential function. So the derivative there is going to be ln of 5, the coefficient, times 5 to the x, the function. And so that's the derivative there. This one here, we can't do the power rule. And it's an exponential function. You would be able to do this using the chain rule, but since we don't know it yet, we're going to do it using some algebra. So what this changes into is it's going to be e to the 1 times e to the x. Because if they have the same bases, then I add the exponent and I'm back to that. So this is going backwards, so this is going forward. So this is what we get. E to the 1 is a coefficient times e to the x. So this is just a coefficient. Coefficients always stay times e to the x, but the derivative of e to the x, the function, is e to the x. So if we want to put it back in the normal one, it's going to be e to the 1 plus x, which is the same as the original. It doesn't always become the same. Just sometimes it does. Okay, so if we change this to be 2x or 2x squared, or if anything else is modified without just the ones, it would actually change it. Okay, so this one here, we have 2, 5. This is just a polynomial. We could just take a basic degree power rule, so that's going to be 10. X to the 4th, so that's kind of easy. This one here we've done before as well, and that's going to be the square root of x, and I take the derivative of it. That is going to change to x to the 1/2, and that is also then going to be 1/2 x to the negative 1/2, and then I put this over 1 because it's a fraction times, and I want to make this a fraction. So then this here becomes 1 over 2 because this one comes down and I get x to the 1/2. So when I do this here, it's going to be negative. I am going to have a 3, so that stays, times this is going to be over 2 square root of x there because you are going to have times 3 over 1, since this one we put over 1 there. And so it's numerator, denominator. And then this one here, that's the trickier one. I'm going to change the color to this one here. If I know this here, this one here, in order to change it, I am going to get, because we're finding the derivative, is going to be 5x to the negative 1, because I need to put that in there. And so when I take the derivative of this, it's going to be negative 5x to the negative 2. And so what that becomes is, I'm just going to write that, plus 5x to the negative 1, and that becomes 5x to the negative 2. I'm just going to erase it from here, and I am going to then say that's going to be 5. This is going to be over 1, and so this one has to go down, and so I have 5 over x squared. Now, this is when it's a derivative. Just keep in mind that that's when it's a derivative and we're going forwards. And so that is going to be the derivative of that. This one here, when we take the derivative of this one here, notice how it's the leading coefficient that's negative. And so we went over the rules before on the derivative there. So the negative 1 stays, and then the derivative of cosine, because the negative 1 is the coefficient, the derivative of cosine is negative sine of x. So the derivative here is actually going to be sine of x. Very good. So now here, if we look at this, there's a reason why I went back and did this here. This one here is the antiderivative. So this here, we just did it doing the derivative going forward. This one here is the derivative. It's the original. Well, it's the antiderivative, so we're going backwards. So while this we found, here, this was when we taken this was the distance function. This one here, this one here was the velocity function. That's our derivative, right? So that's what we have. That's what we got. Here, this one here is our velocity function now. And what we want to find is our distance function. So this is going backwards there. So that means that we're doing the antiderivative. And so the rules have to be pretty much the same. And we could just sort of think of the integral going backwards. So it's it's like it is the integral. And so we're going to take these individually. So 2x to the fifth. When we do that, we are going to take the 2, the x, we're going to add plus 1 there. So we get 6 all over 6. So this one here is going to give us x to the 6 over 3. So the first one is going to be x to the 6 over 3. Then the second one here, that one there is going to be a little bit different. So what we were going to do is we're going to change that to negative 3x to the 1 half. You still have to do that. And so this one here is going to add 1 here, and then you're going to divide that. And so you're going to get, sorry, when you calculate that, it's going to be, oh my goodness, 3 halves. So you're going to get that. But remember when we said before where you multiply and divide it? So that's going to like do the reciprocal on there. And so you're going to get negative 6 because it's 2 times the negative 3 because you're multiplying by the reciprocal. And this is going to x to the 3 halves over 3. So what happens is that these actually reduce and you end up with negative 2x to the 3 halves because these reduce. And so what we end up here is going to be minus 2 square root of x to the third. So that's the antiderivative there. And then this one here, we would think that we would have to do the antiderivative, but it's just the little rule that we had before. If there's just an x in the denominator, what happens if I want to do the antiderivative, as most students do, where you have this, and then you're going to add 1, but that gives you x to the 0. So that's just going to be 5. But that doesn't work because I can't get the answer. If I take the derivative of this, I'm not going to come back to that. So that's not how you do it. This here, you have to remember, 5 is still the coefficient. So that still stays. But this one here is going to be 5 times 1 over x. Well, that there is ln of x. If I take the derivative of ln of x, I get 1 over x, and that's going to be the 5 there. And then the last one here is the trig rule going backwards. What is sine of x? But we just did this over here. So we just did that over here. So if I have this to be the sine of x, and I'm going backwards, so this here is the derivative, and then this is the original function. That means this is your derivative down here, and I want the original function is going to be negative cosine of x. So my last thing to do is negative. It's going to be negative cosine of x, and that is your derivative. So let me move this one over here. So that is going to be negative cosine of x. So these are done using the antiderivative of the power rule going backwards. This here is just knowledge of when you take the derivative of ln of x, what it's going to equal and go backwards. Same thing with the trig rules. What's going to happen if you go backwards? And so that is that. And then here is taking the derivative of this function here. So how do I take the derivative of that? We take one individually. Now, ln of 3 is a number. So this is saying 1.09 dot 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 to the x power. So the ln of 3 is an actual number. So what you're going to do here is you're going to do the exponential rule, which is going to look a little crazy, but not too bad. So it's going to be the derivative is going to be the base, the ln of the base. So it's ln of the base, ln of 3, which is what the base is, and that's going to be the coefficient, and then you're going to do times ln of 3 to the x. So please note, this here is your original function, and this part right here is the coefficient, which is going to stretch or shrink our original function. That's what exponential functions do. So here's the base. If you really want to look at it, it's going to be the ln of 1.09, because that's what, of 1.09 of of x. That's what you're saying. So that's what it means with the ln in it. But we write it this way. And then plus this one here is now going to be to the coefficient times the derivative of ln of x, which is the argument, 1 over the argument, which in this case is x. So the easier way to write that is just going to be over x. And then the derivative of the tangent is going to be just secant squared of x. And that is your derivative. So keep focus on whether it's asking you for the antiderivative, the derivative, and what these rules are. And there you go.